pure Nash equilibria and the iterated elimination of dominated strategies are two interesting game-theoretic solution concepts. But both have a significant drawback. They cannot be applied to all games. There are games which cannot be reduced through the elimination of dominated strategies, or even the elimination of weakly dominated strategies. And those games also do not have any pure Nash equilibrium. For this reason, I will now tell you about one of the most important solution concepts we will discuss. It's called a mixed Nash equilibrium. But before we get to that, let me show you that there are indeed games for which everything we have discussed so far fails. It's a simple game that is usually called matching pennies, but that I like to call the poisoned drink game. In this game, Alice and Bob take a drink. Each of them have a glass in front of them. While Bob is not looking, Alice puts poison in one of the glasses, either her own glass or the glass in front of Bob. Bob then gets to decide whether both of them will drink from their own glass or whether the glasses are switched before they take a sip. So each one drinks from the other player's glass. Writing down this game, it looks like this. Now, if Alice poisons her own drink and each player drinks from their own glass, Alice gets the poison and therefore a payoff of -1. Whereas Bob does not get poisoned, and so he wins and gets a payoff of 1. If Alice poisons Bob's drink and each player drinks from their own glass, Bob gets the poison and therefore a payoff of -1, whereas Alice does not, and so she gets a payoff of 1. And so on. What will happen in this game? Who will end up drinking the poison? We can see that the game has no pure Nash equilibrium by marking all the best responses again. So whatever outcome, whatever strategy profile we look at, the player that drinks the poison is going to be unhappy with their choice of strategy. So what can we do? How would you approach such a game? A plausible thing to do for a player in this scenario might be to just pick a glass at random. For example, rather than committing to one of her strategies, Alice could throw a coin and then poison her own drink with a probability of 50%, and poison Bob's drink with a probability of 50%. This is called a mixed strategy, because Alice mixes between several of her pure strategies. A mixed strategy of a player I with strategy set Si is a probability distribution over Si. We can write down a mixed strategy of player I as a size of Si dimensional vector in which each entry is a probability that the corresponding strategy from Si is played. For this to work, the entries of the vector, of course, have to be non-negative, because negative values don't correspond to any probability. And also, all the entries of the vector have to sum up to 1, because otherwise it's not a probability distribution, right? We have to take some action for sure. We write delta to the power of size of Si to denote the set of mixed strategies of player I. This is also called the mixed strategy simplex. If the size of Si is 2, so player I has 2 strategies available, then we can picture this mixed strategy simplex as a line. The left end of the line corresponds to the mixed strategy in which the first strategy of the player is played with probability 1. And then the other end of the line, the right end of the line, corresponds to the mixed strategy in which the second strategy of the player is played with probability 1. All points in between this left and right endpoint correspond to some mix of the two pure strategies. For example, in the middle point of the line, like right in the middle, this corresponds to the mixed strategy of playing the first and the second strategy with probability 1/2 each. If a player has 3 strategies, so if the strategy set has a size 3, then we can picture the mixed strategy simplex as a triangle, where the 3 corners correspond to the 3 pure strategies. And if a player has 4 strategies available to her, then we can picture the mixed strategy simplex as a tetrahedron, and so on. And this also explains why this is called a simplex, because a simplex is simply the generalization of a triangle or a tetrahedron to arbitrary dimensions. With this concept of mixed strategies, we can now introduce this new solution concept called a mixed Nash equilibrium. It's similar to that of a pure Nash equilibrium, but this time we make use of mixed strategies instead of pure ones. So the players simply can mix between their pure strategies as well. Now, roughly speaking, a profile of mixed strategies is called a mixed Nash equilibrium if no player can gain, on average, by unilaterally deviating from her mixed strategy. So a mixed strategy profile simply means that each of the n players picks a mixed strategy. We can write this, say, as sigma, which then corresponds to n mixed strategies of the n players, sigma 1 to sigma n. And that just means that player I chooses sigma I as their mixed strategy in this profile. Now, in such a strategy profile, a mixed strategy profile, the expected payoff that player I gets, we will denote as pi of sigma. It will later be convenient to be able to refer to a mixed strategy profile, but to exclude one of the mixed strategies of one particular player from this profile. So for this, let sigma minus I denote the strategy profile sigma, but without player I. And then we can add to this profile back a mixed strategy for player I. So we can get back to sigma by writing something like sigma is just equal to sigma minus I plus this mixed strategy for player I, so sigma minus I and sigma I. Now, with this notation, we can define formally what a mixed Nash equilibrium is. A strategy profile sigma star is a Nash equilibrium if for all I, where I is between 1 and n, for all sigma I from the mixed strategy simplex of player I, we have pi of sigma star minus I combined with sigma star I is at least as large as p of I from sigma star minus I combined with sigma I. All this is saying that for each player I, we must have that the expected payoff that the player gets is at least as large when the player plays strategy sigma star I as it is for any other mixed strategy that the player could choose, given that all the other players stick to their mixed strategy in this supposed Nash equilibrium. In the following, I will not always explicitly use the word mixed when talking about Nash equilibria. So if I say Nash equilibrium, I always mean a mixed Nash equilibrium. If I only mean pure equilibria, I will specifically use the word pure. And this is just because mixed Nash equilibria are just the default. We will use them much, much more. So it would be inconvenient to use the word mixed every single time. There's an alternative characterization of what a mixed Nash equilibrium is as well. And this is based on the observation that Nash equilibria are exactly those strategy profiles in which each player only plays those pure strategies with a positive probability that are a best response to the strategies chosen by the other players. So this is the alternative definition of a Nash equilibrium. A strategy profile sigma star is a Nash equilibrium if and only if, for each player I, each pure strategy of this player I is either played with probability 0, so it's never played, or it is a best response to sigma star minus I. More formally, for all I, where I is an integer between 1 and n, for all Si, from Si is just the pure strategy of player I, we have that sigma star I of Si, by which I mean the probability that player I chooses strategy Si in this mixed strategy sigma star I. So this probability is 0, or the payoff that the player gets by playing pure strategy Si must be the highest payoff that the player could possibly get by playing any strategy. So this is what a mixed Nash equilibrium is. We've seen two different characterizations of mixed Nash equilibria, which are equivalent to one another, and you should really make sure that you fully understand what a mixed Nash equilibrium is, because it's arguably the most important concept that I will tell you about in any of these videos.